Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 4 and it is application of Schrodinger wave equation. We have already seen in our previous sections or previous lectures what is the meaning of Schrodinger wave equation, time independent and time dependent. Solution of Schrodinger wave equation gives us wave function. Wave function also gives us the probability density function and therefore gives us the probability of finding the particle between point A and point B. However, we also learned that these wave functions should be finite, single valued and continuous in the region of interest. We also saw two case studies, and one was your finite potential well and there was an infinite potential well. And we saw that the infinite potential well, the probability of finding the particle outside the potential well rapidly goes to 0, whereas when you have finite potential well, it gradually goes to 0, and that is expected also, right? But then it tells me therefore that there is a finite probability of finding the particle even beyond the potential well, where the potential is very, very high. With these basic backgrounds, let me now come to a point where I will explain to you some other case studies with respect to Schrodinger wave equation, and then take forward the concept of this quantum potential, this potential or wave function, and we move ahead and we try to find out the next particle, which is how can we therefore use such a knowledge in deriving the issues related to semiconductors. So as another case study, let us look at a step potential function, right? We have again taking it from Niemann only, and this book is quite a decent book and used across the world. And this is basically a step potential function which we are referring to. Step potential function, as you can see, is when you add x equals to 0 and beyond in the negative direction, your potential is 0, and then suddenly it rises at x equals to 0, so step function, and then becomes constant beyond x equals to 0. So there are two regions of operation here. One is region 1 if I say, and there's a region 2, right? Now let us assume that the particle electron is moving here under two conditions. One is greater than V0 and is less than V0. If it is greater than V0, then there is no problem, obviously, since the energy of the particle is much larger than V0, it will easily pass through and the wave function will not change between the region 1 and region 2. Let us suppose assume an electron or a subatomic particle moving from region 1 to region 2 whose energies are less than V0, then there will be a problem. Not a problem, but it will not be as easy as the fact when energy is greater than 0. So we have two cases. Energy case number 1 is E greater than V0, possibly not discussed with you in detail, but we will be discussing the case when E is less than V0, right? And then from wave function point of view, how does it comes into picture? What you will see here, since this is a 0 potential well, I will have, let us suppose, the sinusoidal wave function coming into picture and then striking here. And as it strikes at this particular point, since the potential barrier is very, very high, there will be a change in the wave function, and the wave function might look something like this. Let us assume it looks like this, and it goes down to exponentially goes down to 0, high values. So it has got a finite value of availability here, because this psi will have certain value. If you multiply with psi star between this region and this region, you will have finite probability of finding function. And therefore you have to ensure that the wave function is also not only they are continuous themselves, but they are also continuous across the boundary, potential boundary, right? And if there's a discontinuity, then obviously the whole system will not be able to work properly. So you need to ensure that there are continuity across all the regions. Now if we graduate from step potential to an infinite potential well, then let's see how it works out. For example, on a hydrogen atom problem, right? We already know that in a hydrogen atom or in any atom formulation, there are principal quantum numbers across which you will have large number of particles available. So for example, if you look at the leftmost the state, then at n equals to 1, this is the energy. N equals to 2, you have a discrete energy. N is equals to 3, again you have a discrete energy. N is equals to 4, again you have discrete energy. And these discrete energies are separated by this sort of a forbidden energy gap. You can't have any electrons available within this energy range for all practical purposes, right? And they will be only concentrated in this and this. You will ask me, from where did you get this equation? You multiply psi x, you multiply the complex conjugate with the wave function, and then you try to find out in this region, and this will give you the probability of finding to be maximum at energy is given by this, and that energy of unit is given as pi square into h cut square divided by 2 m times a. This is a, right? Now as you can see, therefore, quite interestingly, that if the value of a goes on increasing, right, which means that if this potential well has a dimension of say 10 angstrom and you have dimension of 100 angstrom, then what happens is that this a square factor, which was initially 100 in case of 10, will become 10 to the power 4. So 10 to the power 2 and 10 to the power 4 it will become when a equals to 100, which means that there is a 2 order of increase in the denominator, primarily meaning that the energy will decrease by an order of 2, right? Which means that if the width of my barrier or the width of my potential well goes on increasing, these energy bands or these energy values will all come closer to each other, and the reverse is also true. Therefore, if you squeeze it to a low value of a, these will be getting separated out very easily. Let's come to the wave function now, which is the second figure. If you look at the wave function, it looks something like this, and therefore if you can correlate this with the last one, which is the probability of finding the electron here, you see it is something like this, which means that between x equals to 0 and x equals to a, the maximum probability of finding the particle is somewhere in the middle of the particle. However, and this is where interesting things comes into picture, however, as n from the first energy level to the second energy level when you go, now you have two humps available, right, which means that the maximum probability of finding the particle is at these 2 points, whereas this is 0 at this particular point. And therefore, if you move forward in the same dimension, then you will see that for every even values of the energy function shell number n is equals to 2 and n is equal to 4, at the middle of my potential well, the probability of finding it 0, and for every odd in the middle it is maximum, right? So try to find out what is the reason. These are leave as an exercise for you. I will not teach in the class because it is not required at this stage, but if those who are interested can look into it in a much more detailed manner. So this gives me the probability of finding the electron, and therefore the probability of finding the electron is maximum at this, at this, at this, at this 1/4 of the region, and this is 1/3 of the region, this is half, this is single. And from here I can do an a priori prediction of the probability of finding the electron in a potential well. Now till now we were actually looking into 2 dimensions only, x and t. However, in reality when you apply the wave theory to atoms, it's basically a 3-dimensional spherical coordinate system. You need to translate your 2-dimensional or 1-dimensional Schrodinger wave equation. So that's what is written here, that the wave theory extension to an 1 electron system, for example hydrogen atom, this will provide a detailed quantum mechanical framework for understanding the behavior of electron in the atom for sure. And therefore this was the time dependent 1 electron system in a 3-dimensional spherical coordinate system, and it's given by h cut square by 2 m0 del 2. So this is del 2 psi del x2 r theta phi, not r, del r plus vr psi of this into e times psi of r theta phi. R theta phi are the basically the spherical coordinate system across which the atoms can be replaced. An electron and a proton, or 2 opposite charges, are situated at a distance. Potential energy is given by Vr equals to minus e square by 4 pi epsilon naught, and therefore if you want to plot Vr with respect to r, it will always go on becoming smaller and smaller for large values of r. And negatively, so r, if you go on increasing, then this negatively this value will go on becoming more and more high, right, and the energy will go down in that case. So potential energy will go down. Now in spherical coordinate system, this del square, which is basically the Laplacian operator, can be written in the form which is shown here in the slides. These are standard mathematical notations which we use. Now what we do is we pick up this and place it at the Schrodinger wave equation, which is something like this. Looks complicated, but if you look carefully, it is almost the same as what you have learned in the 1-dimensional spatial coordinate system Schrodinger wave equation. This is E minus Vr. E is the energy minus the potential of the particle, and this is multiplied with psi. Psi is the wave function. This wave function is again dependent on r, theta and phi, all the 3 variables. Typically in all the differential equations which are known, we generally do it by separation of variables, which means that we assume that psi of r, theta, phi, right, can be broken down into say 3 variables, this and this, and then we take these equations, place it back into the Schrodinger wave equation, try to find for 1 by making other two 0, and so on and so forth. This is the mathematical sort of a methodology by which we do it. As an example, if you take psi of phi to be equals to this equals to 0, so I get this equals to 0. This is basically a one-dimensional sort of a Laplace equation. Solve it and you will get the various values of phi. Now, if we look carefully, the quantum numbers are known to us, right? So, we already know there are 4 quantum numbers, and if you solve this equation, this one, the first one, then I will get solution to be equals to e to the power I m phi. So, I will get phi of phi to be equals to e to the power I m phi, where we already know m is defined as the magnetic quantum number, and we have this phi is already known to you. And this m should be an integer value. So, it will be 0, plus minus 1, plus minus 2, right. And if you do not assume this to be as an integer value, then we will always have multivalued function for the phi of psi, and that will be the, and therefore this is not allowed in a sense, right. Now, we already know that the discretization of energy level is already there in terms of n, and therefore the energy levels of a hydrogen atom is given by this expression here, right. And a hydrogen atom is a single electron system, and if you look very carefully, when n equals to 1, so if I assume this to be constant, not assume, it is actually a constant value, then En is directly proportional to minus of 1 by n square. So, when n equals to 1, then I get E to be equals to En to be equals to some x which is constant divided by 1. If it is n, this is for n equals to 1. If n equals to 2, then I get En to be equals to minus x by 4. If n equals to 3, En becomes equals to minus x divided by 3, 3 is 9, right. And so increase parabolically will happen. And so, higher the shell number, or in a sense quantum number, principal quantum number, negatively it goes on increasing, right. Negative it goes on increasing, and the energy levels of the hydrogen atom are therefore quantized in a sense. And therefore, if you remember our previous discussion where we were discussing the energy level of a hydrogen atom, you can see it is n equals to 1, 2, 3, and they are basically quantized in a sense. Quantized means they have the fixed value, and any electron coming here either has to sit at n equals to 1 or at 2 or at 3. We cannot sit at any intermediate positions, right. And therefore, this is basically a constant sort of principal quantum number available to us. So, let us look at the radial probability density function, another term which many people follow. And radial, why is so? Because in an atom, let us suppose this is my positive side and the electron is moving across this. My classical mechanics tells me that the electron will be moving across this elliptical or circular path across the positively charged nucleus. However, you very well know that this is not true. What is true is that associated with this electron there will be a cloud, and this cloud will have a wave function like this. And if you find the psi star is the probability of finding the electron within this region of operation, within this small region of operation. Now, if you see the left hand side here, the first figure, then you see that when n equals to, or r by a naught is the, r is the radial distance from the nuclei, a naught is some constant which you take up, then at n equals to 1, you get this to be as maximum here. You get the maximum radial function available here. Why? Because very simple and true, that is the point where you will get the maximum electrons probability function. But then quite interestingly, unlike the discussion which we are having just now, the probability density function actually falls down very steeply as you move away from n equals to 1, and it falls very quickly to almost very low value, right. And that shows that the radial probability density function for a 1 electron atom is the lowest state is given by this. And then for the next higher state, when n equals to 2, you will see, remember n equals to 2, you had 0 probability function at n equals to 2, and that is what I got here. You see, this is basically 0 which you get, right? The probability is actually 0 at n equals to 2, and it shoots up at n equals to 5 approximately. So, this gives you a brief idea. Even if you do not understand, these are slightly ahead of your times, those who are new to this domain. Please understand one basic, two important points, takeaways. One is that the discussion is always limited to the fact that there is a probability density function, be it radial or non-radial, does not matter, but it gives me an idea about the probability of finding a particle within a space, right. In the absence of an external energy, in presence of external energy, doesn't matter, we just fit that value into the Schrodinger equation. So let's look at a numerical approach so that we can consolidate our understanding, right? So you are told to calculate the first 3 energy levels of electron in a hydrogen atom. One electron atom is basically a hydrogen atom. Now the energy is given by En equals to minus m0 e to the power 4 divided by 4 pi epsilon naught square into 2 h cut square by n square, right? Now if you solve it, out of all these terms, this part is actually a constant. m0 is the weight, E is the electronic charge, h cut is already known to you, is a modified Planck's constant, epsilon naught is known to you, pi is always known to you. And if you feed it here, right, if you feed it here, what I get is I get minus 13.58 divided by n square times electron volts. So when you take n equals to 1, I get minus 13.5 electron volt, and then I get E equals to 2 minus 3.39, and then E equals to 3 1.59, because it is parabolically falling function. Why? Because it is divided by n square. So when n goes from 1 to 3, n square goes from 1 to 9, and that's the reason you see that the energy starts to fall down, which means that for n equals to 3, the energy level is very small. So you actually require to give a smaller energy from outside to make it free. So when you want to make something free, you want to ensure that its total energy is actually equals to 0. If it's a bound state, then energy should be negative. Now if you want to make, for example, electron which is kept at E1 to be free, you need to give an energy from an external system. How much? Plus 13.5 electron volt. However, if the electron is sitting somewhere in the third batch, at the third n equals to 3, then I have to give just 1.51 electron volt to make it free. That's the reason why electrons in the outer periphery is much easier to extract it outside, because it is under the less influence of nucleus in a general sense, right? And that's the numerical approach I wanted to show to you as far as this is concerned. Now this you must have studied, I will just quickly go through it. And this is the formulation of the periodic table for hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. The n values are given, which basically tells me how many number of shells are there, and corresponding L values are there and M values. So all of you must be aware of that there are 4 principal quantum numbers associated. This is N, L, M and S. S is the spin quantum number, M is the magnetic quantum number, L is the azimuthal quantum number, and N is the principal quantum number. Now depending on the values of this, I can get other values in a sense. To a larger extent we can easily get it. Now we are assuming that M equals to 0, but M can have values minus 1 as plus 1. For every value of M, we will have plus half, minus half as the spin quantum number. Though this will be not directly utilized in your study of this particular subject, but a basic knowledge will be helpful somewhere or other. But so don't take this slide in very much detailed manner. This will be more useful for those people who are studying chemistry or quantum chemistry in that sense. But just for the completeness sake, I presented you the periodic slide. So let me come now to a point what we have finished till now. So let me recapitulate what we did so that you are aware of, and then we can move to the next maybe section. What we have done is I have started with a step potential well, right? And then we took a step potential, not a well, but step potential, and we saw that if this is the electron wave function and then this is the exponentially decaying function, this will be decaying very fast, and this is a free waveform. I look at it sinusoidal waveform. So most of the time when you will have free waveforms, free means that it is not under the influence of an external electric energy. It will be more or less a combination of sine and cosineal, and therefore I can represent it by a sine wave. Whereas when it falls under a region where you do have some amount of input in terms of potential, it becomes exponentially decaying function, right? So this is what we have learned in the step potential problem. Then we went for a hydrogen atom problem, and this is basically a 1 electron system which we studied. And within the 1 electron system, we looked into the fact how energy is related to the, we looked into 13.6 divided by n square, where n is the number of shells at which you are trying to plan out. And we saw that if you move to a higher number of shells or higher number of shells, there the energy becomes negatively small, and therefore from an external world you require to give a lesser amount of energy to make the particle free, whereas if the particles are very close to the nucleus, you require to give a much larger potential in order to make it free. We learned this from an energy potential diagram. We also learned that if you have a potential well problem, then for odd values of n, in the half points, half a by 2 points, you will have the maximum probability, whereas for even shells you will have probability equals to 0, and that's where I told you to have a look into it. You might study it independently and see why the statement is correct in this case. Then what we learned across in this case was, we learned that there are also radial Schrodinger wave equation or spherical coordinate Schrodinger wave equation, because in all the practical aspects you will always have radial or spherical coordinate systems r theta phi, and then breaking the variables in terms of r theta phi, we were able to get the values of this psi, and from that psi I can extract the value of my probability density function. So this is the basic generic idea for any of the two structure, be it spherical or linear coordinate systems. What we will do in the next turn is, we will use these techniques and try to ascertain or get an idea about semiconductor. Within semiconductor, how can we put inside it, right? And then we can move ahead. So I think we'll stop here today, and thanks a lot.